Okay, welcome back. So today we shall continue with our discussion. Last class we discussed electrochemical cells and we looked at electrode potentials. Today we shall look at the factors affecting electrode potential. And after then we'll discuss our major topic for today, which is the NERNST equation. So factors affecting the electrode potential. First, you need to know that by convention, the half equation of any reaction is written with the reduction as the forward reaction. If I ask you to write the forward reaction of any chemical cell, the reduction is to be written as the forward reaction, and then the backward reaction is the oxidation. The magnitude of the electrode potential depends on the position of the above equilibrium. When the value is positive, it means a forward reaction is favored. So if the value of the electrode potential E naught is positive, which we shall see when we begin to solve for the next equation, the value is positive, then it means it favors a forward reaction. And if it is negative, it favors a backward reaction. Now let's see some of those factors that will affect the electrode potential. The first is the nature of the metal. The nature of the metal will determine whether the reaction will favor a forward reaction or a backward reaction. When a metal is highly electropositive, the metal atom have a greater tendency to become positive ion. So when a metal is highly electropositive, and you know across the periodic table, electronegativity increases. So it means the elements that are found on the left-hand side of the periodic table, mostly the halogens, that is the group 7, the chalcogens, the group 6, and then group 5 elements. Then the ones on the right-hand side, majorly the first, second, and third group, or that's the sodium, calcium groups, those are highly electropositive groups. So when a metal is highly electropositive, the metal atom have a greater tendency to become a positive ion, leaving the electron behind the metal electrode. So because it wants to become a positive ion, the implication is that it will have to lose electrons. So it leaves the electron at the metal electrode. The electrode potential therefore become more negative, and the position of equilibrium shifts to the left, because we said when we have positive E naught value, it means that it's going to be having favoring the forward reaction, which is going to be a reduction reaction. In this case, it will favor the backward reaction, that is, move the equilibrium shift to the left, becomes an oxidation reaction. So you can see an example here. Silver here, this silver plus E minus to give us Ag. You can see the electrode potential is positive plus 0.80. But when we move on to lead, which is more positive than silver, lead is Pb2 plus, losing 2 electrons. You can see the E naught is what? 0.1 minus 0.13, negative, meaning that it's going to favor the left reaction, and consequentially, it is going to have the value to be negative. The E naught value will be negative. For zinc also, you can see our electrode potential value is also negative, so it will favor the left reaction. The reaction will shift to the left, and it will favor the oxidation reaction. The same thing with magnesium, Mg2 plus 3 minus to give us Mg. You can also see it is negative. So as the positive value of that, the nature of that particular metal, as the electropositivity is increasing, you can see what is happening to our electrode potential value. Electrode potential value is getting more negative. You can see from 0.80 went to minus 0.13 to minus 0.76 to minus 2.38. Another factor that will affect the electrode potential is the concentration of the metal. If the concentration of the hydrated metal ion is increased in the equilibrium, the position of equilibrium will shift to the right, favoring the forward reaction. So whenever we increase concentration of the hydrated metal ion, the reaction will shift to the right, and it will favor the forward reaction. So electrode potential therefore will become positive. Let's see in the case of lead, you can see Pb2 plus 3 minus give us Pb solid. Our value is what? Is negative, minus 0.13 volts. That's at our 1.0 mole per dm cube concentration. That's the normal situation. But let's see now, if the concentration of lead changes from 1.0 mole per dm cube to 0.001 mole per dm cube, equilibrium shifts to the back. That means shift to the left. That is, it favors a backward reaction. The equilibrium will shift to the left, favoring a backward reaction. Your electric potential value will be less than minus 0.13 volts. But if the concentration is increased from 1 to 10 mole per dm cube, that is 10 molar, equilibrium will shift to the right, and that will favor a forward reaction. Therefore, your E, which is your electric potential, will be greater than minus 0.13 volts. Another factor is temperature. Most of the reduction processes are exothermic processes, and the meaning of an exothermic process is one in which heat is evolved. That means it involves a lot of temperature. Increasing the temperature will cause the equilibrium to shift to the position of endothermic process, because exothermic processes on their own releases a lot of heat, so they do not require a lot of temperature. They have enough heat to carry out, to undergo their own processes. So if you are increasing the temperature of such a reaction, it is going to be favoring the endothermic process, which is to the left. Thus, the electric potential becomes more negative and less positive. Of course, you know what happens when it is negative and when it is positive. Also, pressure for gaseous species is another factor. For gaseous species, pressure will also is also a factor that affects the electrode potential. This applies only to gases. From what we have learned from the chemical equilibria, when pressure is increased, equilibrium will shift to the position with less mole of gases. So it will shift to the place we have less mole of gas, while decreasing pressure will cause equilibrium to shift with the area where we have more mole of gas. For example, if you see in chlorine here, this is a chlorine gas plus 2E minus, becoming this chloride ion. You can see the electrode potential is plus 1.36 volts. If you increase pressure, it will cause equilibrium to shift to the right, and therefore the value will be greater than 1.36 volts. But if I decrease the pressure, equilibrium will shift to the left, and then I'll have my electrode potential to be less than 1.36 volts. These are the things you need to take note of. Once you know the effect of that particular, whether it is temperature, pressure, nature of the metal, once you know the particular factor, you must be able to tell whether it will shift the equilibrium to the right or to the left. These are the major things that you need to know from all these factors we are discussing. So now let's discuss our major topic for today, which is the NERNST equation and its application. The NERNST equation and its application. All the electrochemical cells that we have discussed so far, they have what we call standard electrode potential. And what is standard electrode potential? It is the electrode potential at 25 degrees Celsius or 298 Kelvin, 1.00 atm, which is atmospheric pressure, and 1 molar concentration. Once we can achieve this, it means that we're having what we call a standard electrode potential. Now, if concentration of ions and temperature change, it will affect the value of electrode potential. At this moment, we can use an equation to study the changes of concentration of ions using the NERNST equation. So sometimes temperature changes, pressure changes, which in fact on the most common situations, we don't have an ideal situation whereby your temperature will be a perfect room temperature, 25 degrees Celsius, perfect atmospheric pressure, 1 atmospheric pressure, and you have 1 mole per dm cube. No, most times this is not the case. So how do we calculate the actual electrode potential when we know the standard, and vice versa? So the equation that helps us to address such a problem is what we call the NERNST equation. And this is the NERNST equation. This is a very, very important formula that you need to commit to memory. You can see our E, which is your electrode potential, is equals to your standard electrode potential. You can see that now that's your E naught This is your electropotential for the cell. This is the standard electropotential at these conditions. This value this value will be given to you because this value is a standard value for all electrochemical cells, plus RT over NF, ln of the concentration of the reactant ion raised to the power of the number of moles all over the product ions concentration of the product ions raised to the power of the number of moles. So this is the formula for your NERNST equation. We'll solve several questions to buttress this fact. Your R, which is your ideal gas constant, T is your temperature, N is number of moles, and F is your Faraday's constant. Your R, which is your ideal gas constant, will always be given to you. It has a value of 8.314 joule per mole per Kelvin. Temperature, which is regularly supposed to be room temperature. If it changes, you'll be given the value, 25 degrees Celsius, which is same thing as 298 Kelvin. Your F, which is your Faraday's constant, is given by 96,500 coulombs per mole. So if we should input these standard values in this equation to simplify the equation, since we already know R is 8.31, we know T is 298. Of course, we know our Faraday to be what? To be 96500. So since we already know that, it means we can convert this. Now the value you are seeing here, which is 2.303, is used to convert ln to log. You can see in the original equation here, we use ln, and you can see in this equation I have here, I'm using log. So the relationship between ln and log is 2.303. So 1 ln is equals to 2.303 log. So that is why I'm multiplying this value by 2.303 to convert it from ln to log. If I do the mathematics, if you punch your calculator correctly, you are going to have 0.059. 0.059. So instead of having this long formula, which I would advise you to still know, you could just use this summarized one, which has already calculated your RTF. All that you will need now is the N, which you will get from the equation that will be given to you. So E will be equals to E naught plus 0.059 all over N log of the concentration of reactant ions raised to the power of their number of moles all over the concentration of the product ions raised to the power of mole. This square bracket represents concentration. In chemistry, whenever you see a square bracket, we are discussing about concentration. So let's see some examples. Let's see some example. Example number 1, we can see silver chloride ion with a concentration already given to be 1.5 mole per dm cube. So the equation for the reaction is this, which is given. I will give you, if I give a question of this kind, I might give you this equation, I might not. If I don't give you the equation, it is obvious that this is silver moving from, this is 0 state silver, and this is a silver in the +1 state, meaning that silver lost 1 electron to become silver solid. So Ag plus E minus. As I told you, you put the electron at the side with more charge in order to balance the charge. You can see now the charge on this end now is 0. The charge here is +1 minus 1, which is also 0. So, and we're giving the E naught to be equal to plus 0.80 volts. This value you will be given, E naught, which is your standard electropotential. Now, from the standard electropotential, I can see this is a plus. Because it's a plus, it has already suggested to me that this is a forward reaction, favors a forward reaction, and this particular equation is supposed to be a reduction, not a oxidation. So you can see that I know this is how the equation will look like only by looking at this value. This value is positive, meaning that this is a reduction reaction, and you can see this is how to write a reduction reaction. If I wanted to write it as an oxidation, I would have written it the other way around, putting silver solid on the reactant, and then silver ion plus the electron on the product side. So now this is E is equals to E naught plus 0.059 all over N log. Now this is the formula. The only thing I'm changing now is log of, don't forget from the formula that I showed you, say we are going to have reactant raised to the power of the number of moles all over concentration of the product. So let's see, what's the concentration of the reactant? Is this is the reactant. Of course, you know this here is just our electron. We can't include this. This is not a reactant. Our reactant here is Ag plus. So this Ag plus. What is the number of moles? You can see with it, nothing is written, no coefficient is written in front of it. So that is telling us that the number of moles will be 1. Is that okay? Whenever you don't see anything written there, it is 1. That's why I've written 1 here, which is not also necessary, but just so that you can see that the value is 1. That's why I put it here. Now divide by the concentration of the product. Now look at the product. The product here is a silver solid. Is a silver solid because you can see it's not carrying any ion, it's not ionized. Whenever we see solids, the concentration will be 1. Whenever you see a solid, the concentration will be equal to 1. You will not be giving concentration for a solid because solid cannot have a concentration. The ion is one that will have a concentration because it is in an aqueous solution. It has been dissolved in water. But the solid will be having a concentration of 1. That's why the value here is 1. Now this value has also been given, which is E naught, which is 0.80 plus 0.059. Don't forget 0.059 was calculated from RT all over F. If you know you can't remember this value 0.059, solve it yourself. Multiply the value of R times T divided by F. Those values will always be given to you. So, but if you can remember this, it will save you a lot of time. Log 1.5 raised to power 1 divided by 1. So E will therefore be equal to 0.81 volts. Don't forget, you must solve your log first before you solve this. So it means you find the log of 1.5, multiply the value by the sum of 0.059 and 0.8. You are going to be having 0.81 volts. You multiply 0.05 times the log value and add it to 0.80. You have 0.81 volts. You can see the value is still positive, which is what is expected. The E value, which is our electrode potential, will be positive. Since our standard electrode potential is also positive, we are expected to still have a positive value. So if we look on to the next one, let's take this copper and copper 2 plus. Look at the value is also positive. So immediately it has already told me that this reaction has to be a reduction reaction, moving from higher oxidation number to a lower oxidation number. That's 2 to 0. I'll add 2E minus to this place, obviously because I need to balance the charges. Plus 2 minus 2 is 0. This is copper solid on the other side, which is also 0. We're giving the concentration to be 2.0 mole per dm cube. You'll be giving all these values, so it shouldn't be a problem. So if you're asked to look for the E, which is your electrode potential for the cell, for this half cell, you use the NERNST equation. So our E again is equal to our E naught plus 0.059 all over N, where our N is our number of moles. Good. In this previous equation, our number of moles is 1. How did I know that? Number of moles here is telling us the number of electrons that was transferred. Number of moles here is representing the number of electrons transferred. Between silver plus and silver solid, only 1 electron was transferred. But if you look at this case, between copper and copper solid, 2 electrons were transferred, which is our 2E minus. So therefore, our N in this case will be 2. Okay? Our E naught was given as plus 0.34. Now, don't forget this one will be concentration of the reactant, which is concentration of this. You can see the coefficient here is still 1. So that's why we are raising this to the power of 1. This one is also a solid, so it will be all over 1. You can see this is a very, very simple and straightforward calculation. So this is plus 0.34 plus 0.059 all over 2 log of 2.0. Don't forget when you are punching your calculator, you calculate the log of 2.0. Whatever value you have, you multiply it by 0.059 divided by 2 before you add it to 0.34. That's just normal mathematical operation. You solve for your log first before you solve, before you multiply, before you add. Okay, so having said that, there are two other examples here. I would like you to lay your hands on this chlorine, Cl2 to Cl minus. And okay, I will solve this last one because of a little peculiarity that is here. Let's solve for this Fe3 plus to Fe2 plus. You can see both of them, you'll be giving concentration for them because there's no solid here, unlike in the two examples I did before now. One of them was a solid, but in this case, both of them are ions, Fe3 plus and Fe2 plus. So we're giving concentrations for both of them. But of course, you can also see that the E naught, which is your standard electropotential, is also positive. So it means this is also a reduction reaction, moving from Fe3 plus to Fe2 plus, reduction. If you don't understand what I mean by is a reduction reaction, go back to I think last two videos and go and see that video over and over again. So if you've seen that video, you understand why we are having reduction from 3 plus to 2 minus. The oxidation state now here is 3 plus. On this other side is 2 plus. So therefore, we have what has happened is a gain of 1 electron. But in terms of numerical values, it has reduced from 3 plus to 2 plus. So in order to balance it, I want to have 2 plus on both sides. This is 3 plus, so I add E minus. E minus will reduce this value by 1, therefore making this value become also 2 plus, and this is 2 plus, so that's balanced, okay? Not on this other hand. If I put this plus E minus on this end, it will reduce this one, and this one become plus 1, this one will be plus 3. That will not be balanced. So this is where it is supposed to be. Having said that, we'll apply the same equation. E is equals to E naught plus 0.059 all over N log of concentration of the reactant, which is Fe3 plus, raised to the power of the number of moles, which is 1 in this case again, divided by concentration of the product. In this case, the product is not a solid, so it will not be equal to 1. We are going to have a concentration. So concentration for Fe2 plus also raised to the power of 1. So our E will be equals to plus 0.77 plus 0.059 over 1. Log of these values have been given. 0.800 divided by 1.30. So the correct thing now is to first divide these two values, which is 0.800 divided by 1.30. Whatsoever you get, find the log of it. When you find the log, you multiply it by 0.059. Okay, of course, here our number of moles is still 1 because you can see the amount of electron transferred between ion 3 and ion 2 is still 1 electron. So we are going to have 1, and our E naught will be 0.77. So sum that together with the product of these values, and we are going to have plus 0.758 volts. I want to encourage you to make sure you punch these things on a calculator as I'm explaining it, because so many times you think you understand it until you try to solve it on your own, and then you see you start getting funny answers. So try to solve it. If you are not getting it right, follow the order of operation that I just told you, and you are going to arrive at the same answer that I've put on the screen here. So these are other examples. Good. Let's solve this, which is a more test-like example, the kind of questions you should be expecting. If you have an MnO4 minus concentration given, plus H plus, the concentration also given, this slash, of course, that's react to give Mn2 plus, which is 17.0 mole per dm cube. And this equation was also given to you. This is a balanced equation. You can see that we have hydrogen on this end, and we have water on this end to balance the hydrogen. This is also a half equation reaction. It has its other end. I believe while we're solving for half equation, we did exactly this particular one, MnO4 minus. This is a half reaction of it, and you can see this is a positive standard electropotential, which has also suggested to us that it is a reduction reaction. And obviously it's a reduction reaction. If you've not forgotten, the value, the oxidation state for manganese here is plus 5. Oxidation state for manganese here is plus 5. That's a plus 5 value. And the oxidation state for manganese here, obviously, that's 2. So we are moving from a plus 5 value to a value of 2. Is that plus 5 or plus 7? plus 7, plus 7. The value is plus 7 to plus 2. So it has a electron transfer of 5. That's why we have your 5e minus here. But you don't have anything to worry about if you are given the equation will always be balanced. But if you are not given the equation, you have to solve it out using the technique we have already studied in our previous classes. So MnO4 minus plus 8H plus E, 5E minus to give us 4H2O plus Mn2 plus. So how do we solve this? The same way, very straightforward. You can see we have our E naught plus 0.059 all over N log of concentration of reactants. Now, our reactant is more than 1 now. That's the interesting thing. That our reactant now, we have 2, we have MnO4 minus and H plus. So MnO4 minus concentration, you can see the formula says product of concentration. So when you write the first concentration, you also put the next one. What we'll find is their products. We'll multiply them together. We'll also find concentration of H plus raised to the power of number of moles, which is what? 8. MnO4 which is also one of the reactants, is also raised to the number of moles, but the number of moles here is what? 1. So I don't have to write 1 here because it doesn't make any difference. So that's why I put 8 here. All over the concentration of the product. Concentration of the product is Mn2 plus. Okay, Mn2 plus. So Mn2 plus here is also having a charge of 1. Now you ask me, why have I not put the concentration of water, which is also a reactant on this side? Don't forget, the state of water here is liquid. So the value will also be 1. And 1 times anything remains itself. So that's why we have not included it. Whenever we have a solid or a liquid in the equation, then the concentration will be taken as 1. So it will not participate in the formula. You don't have to include it. 1 will not change anything. So you can just leave it out. So that's how we have this formula this way. So if you input the values, E naught is plus 1.52 plus 0.059 divided by 5. You can see the number of electrons being transferred is 5. Number of electrons transferred is 5. And the reason is because the oxidation state of manganese here is plus 7. You can always calculate it. Oxygen is minus 2. Minus 2 times 4 is minus 8, which if you take minus 8 to the other side, it becomes plus 8. And of course, there's minus 1 on the other side, making it plus 7. We've done that in the previous videos. So from here now, E will therefore be equals to this value, 1.10, 0.800 raised power of 8 all over 17.0. Again, you need to follow the correct mathematical operation. You must find the 8th power of 0.800 first, multiply whatever you get by 1.1, then divide their value by 17.0, which is still 17, then find the log. After getting the log, you multiply that value by the by 0.059 divided by 5, and then you sum it with 1.56. You will definitely be having positive value again, which is going to be 1.50. In the case of this titanium, moving from 3 plus to 2 plus, we can see the negative value, which already tells us to be favoring the left. Equilibrium will shift to the left, and therefore it will favor the backward reaction, which will be oxidation reaction. So that is why our final answer will also be a negative value, which is for an oxidation reaction. So the next equation and EMF of a chemical cell. The next equation and the EMF of a chemical cell. Now consider the following redox reaction in a chemical cell. If I have A plus B to give me C plus D, with each of them having PQRS as their number of moles. Is that okay? P is the number of moles of A, Q is the number of moles of B, R is the number of moles of C, and S is the number of moles of D. At 25 degrees Celsius, means at room temperature, the next equation would be given by this, which is the formula I've shown you before, E naught plus RT over MF, ln of the reaction, ln of the concentration of the reactant ions raised to the power of their number of moles all over the product ions raised to the power of their number of moles. So if we should apply that to this 1 here, we are going to be having E is equals to E cell. Our E cell now is what is representing our standard electrode potential. We want to find the EMF, the next equation, the EMF of the cell. That's our E cell plus all these values which we've calculated before. If we multiply the value of R, which is 8.314 times temperature, which is 298, divided by the Faraday's constant, which is 96,500, and then multiply by 2.303 to convert our ln to log. We are going to have 0.059, which is what I've already calculated here, divided by n. We did that in last slide. Now from here, now you can see our log. The concentration of the reactant ions raised to the power of their number of moles, concentration of A, which is this square bracket of A, raised to the power of number of moles, which is P, times concentration of B raised to the power of number of moles, which is Q, divided by that of the product, which is concentration of C raised to the power of R, concentration of T raised to the power of S. Now, for pure solids and liquid, it will not appear in the equation. I said that when we add water, while we were solving, we saw water. I did not include it in the equation because the concentration will be 1. And if I have a pure solid also, it will not be included in the equation because they will have a concentration of 1. All right, so let's see this equation as an example. If I have this equation, this is a full equation of a chemical cell now. The one we've been solving before now was just for a half equation. Now, if we have a full cell now, to solve for a full cell, we are going to solve for each half cells. Is that okay? Except we are giving our E cell directly. But if we are not giving our E cell directly, we can solve for each half cell and then sum them together. But for this question, we're giving our E cell directly, so we could just solve immediately for our overall electrode potential for the electrochemical cell. So let's see how to go about that. The equation gave us this. I told you this is a shorthand of how to write the electrochemical cell. You must be able to write this. This is what we call a cell notation. I explained this to you in previous classes. You can see chromium solid with chromium C3 plus of this concentration. You can also see nickel 2 plus with this concentration to give nickel solid. Okay, so you'll be given the oxidation, the E naught for the oxidation reaction and for the reduction reaction. Obviously, we can see the one that is our oxidation and the one that is our reduction. You can see this positive sign automatically. You can see this is our Cl to give us Cl3 plus. Moving from 0 to 3 plus, that's definitely a oxidation reaction. Moving from 2 plus to 0, that's definitely a reduction reaction. So, by giving a reduction reaction, you will be given the values of your E naught, in the question. Now you are the one to work on to get your total. How do we get your E cell? Your E cell is the E naught for each half cell, E naught for this half cell, and E naught for this half cell. If I sum it together, I'm going to get plus 0.49 volts. So that's how to sum them together. But there's still more work to do here. If I give you these two equations, in order for you to join them together, what am I supposed to do? If you look here very closely, you see that the number of electrons here is 2. The number of electrons here is 3. There's no way I can join them together because the electrons will not cancel out. So what are we supposed to do? Remember what we did when we were solving for half equations the other time. When we're to join them together, we will use the number of electrons here to multiply this equation and use the number of electrons here to multiply this equation. So if I do that now, I'm going to have 2 I'm going to have here now 2 times chromium on this reactant side times the chromium ion on the product side times 3 electrons, which will become 2 here, 2 here. 2 times 3 now will become 6. So if I do the same for here now, I multiply this other equation by 3. This becomes 3 This is 2 times 3 again, which automatically becomes 6. And this is also what? 3. Now, I'll have to join these two equations together. To do so, these 6 electrons will take care of 6 electrons. So 6 electrons carry 6 electrons, cancel 6 electrons. Then here I have my 2 chromium, 3 nickel 2 plus to give me my 2 chromium 3 plus and my 3 nickel solid. If you can't get this overall reaction correctly, there's no way you can arrive at the correct answer. Also, another information I'll get from what I just did now is I'll be able to know the number of electrons that was transferred in the reaction. You can see now the electrons transferred is 6. It is neither 3 nor 2. The answer for the electron transferred is 6. And see, because after I finish multiplying and I balance their number of electrons, we had 6, 6. So 6 is going to be the number of electrons. So if you have done that overall reaction correctly, that's the first step to arriving at the correct answer. So then I would subtract the 2 electropotential. It is going to give me this value plus 0.49 volts. So our E will be equal to E cell plus 0.059 divided by 6. We are dividing by 6 here. Number of moles here is 6, which I've already established. Log of Ni, which is our nickel 2 plus, it's supposed to be log of the product, concentration of the product raised to the power of their number of moles. You can see this one here is a solid, it's not carrying any charge, so therefore we will not include it in the equation, but it will be 1. This one here is not a solid, so it is an ion, so we include it, nickel 2 plus raised to the power of the number of moles, which is 3, okay, divided by, here nickel is a solid, so we do not include this in the equation. We put chromium raised to the power of its number of moles, which is 2. So that's why we have 2 here. So this will be equal to our E cell. We've already calculated it here to be 0.49. So 0.49 is going to be here plus 0.059 all over 6. Log of this value was given. Concentration of nickel was given 0.2 raised to the power of 3 all over 0.010 all raised to the power of 2. Of course, follow the correct mathematical operations. You are going to arrive at plus 0.51 volts. So that is how to go about this question. Okay, this is another question. Also asking for electrochemical cells. The same thing applies. You are given manganese moving from 0 to 2 plus. Of course, that is going to be oxidation. And you are given ion moving from 3 plus to 2 plus, that's going to be reduction. You can see it's reducing 2 plus to 3 plus to 2 plus. So, but don't forget, in this case, you're also given platinum solid. That doesn't affect your equation. This platinum solid is just telling us that the electrode that is being used here is a platinum electrode, because the ion 3 plus and ion 2 plus here, they are not metal. So we are not using ion metals. Using a mixture of 2 ion ions. Is that okay? So we are going to use platinum metal as our electrode. So, having said that, you'll be given the oxidation and the reduction, definitely. I might not give you the equation, but I must give you these two values, which is your E naught for reduction and E naught for oxidation. These two values will be given to you. If you are not given the half equation, generate it yourself, which is very simple. Having generated it, you still need to do the overall reaction. The overall reaction now, the number of electrons transferred here is 1. The number of electrons transferred here is 2. So to balance it, I multiply the second one by 2. I multiply this first one by 1. Multiplying by 1 remains the same, so I don't need to bother myself. I just multiply this by 2. This becomes 2 Fe3 plus, 2E minus, and then 2 Fe2 plus. I can cancel these 2 now. This cancel this. So therefore, if I sum them together, I'm going to be having Mg, which is your magnesium, plus 2 Fe3 plus, which is this, to give me my Mg2 plus, which is this, plus 2 Fe2 plus. I believe that is very clear. Of course, the same thing applies to get your E cell. You sum up these 2. If I sum them up, I'm going to have 3.15 volts. So E is equal to E cell plus 0.05. How many electrons was transferred? 2. You can see we have 2e minus 2e minus, so 2 is going to be our number of electrons, that's number n. Then the log of reactant. Now let's move to the reactant side. Magnesium here is a solid, so it's not going to participate. I'm just going to have a concentration of Fe3 plus raised to the power of 2. Then all over the concentration of the products. In the product side, both of them are ions, so they will both participate. There's no solid on this end. So I put both of them there, raised to the power of their individual number of moles. This is 1, this is 2. So I put 2 here, I put 1 here. 1 is not showing here because it does not affect the outcome of our calculation. So here now, I'm going to have 1.80 raised to the power of 2 all over 0.500 multiplied by 0.750 raised to the power of 2. So follow the correct mathematical operation again. Find the squares of these two, then multiply and divide accordingly. Then find the log before you multiply with this value, and then before summing up with 3.15. If you don't follow that order, you are going to be getting a different answer entirely. So that is how to do the correct calculation. Again, I encourage you, make sure you are punching your calculator right now and arriving at the same answer that I'm displaying here, so that you'll be able to do it on your own when you are given questions of this kind. This is another example. I want you to look at it and solve it yourself. Solve it yourself. It's just the same thing with what we have been discussing before now. Just lay your hands on this and arrive at the answer on your own. Now, next equation and equilibrium constant, Kc. Now, we also have what we call the equilibrium constant. Now, consider the following reaction. If we have this reaction of copper 2 plus 2 solid to give us our zinc aqueous plus copper, and we're giving this E, this value E here for our electric potential, which is plus 1.0 plus 1.1 volts plus 1.1 volts. The Kc, which is our equilibrium constant of the reaction, can be expressed as this. Now look here, our equilibrium constant here is going to be the concentration of the the concentration of the product ions raised to the power of their number of moles all over the concentration of the reactant. You can see this is opposite of what we had in our next equation. In our next equation, it was concentration of the reactant all over the concentration of the product. But in this case, we're having concentration of the product all over the concentration of the reactant. This is going to give us our equilibrium constant. So we can see Zn2 plus all over Cu2 plus in the concentration, because of course you can see this is 1, this is 1, so that's why they are not carrying any powers. And you can see we are not including this for the product, which is zinc 2 plus. We are not including the copper because it is solid, and here for the reactant we are not including the zinc because it is solid. So we are including just this. So that is what we call our equilibrium constant, Kc. As time passed, the concentration of Cu2 plus decrease while Zn2 plus increase. Using standard reduction potential of copper and zinc, we use a standard reduction potential. This is a standard values, you don't need to know them, they'll be given. Cu2 plus aqueous plus 3 minus to give us copper. This is standard reduction potential. When the concentration of Cu2 plus decrease, equilibrium will shift to the left. See that now? Because our E naught is positive. When the concentration decreases, equilibrium will shift to the left, and our E naught will also decrease. We already said this when we're talking about factors that affect electrode potential. Therefore, our zinc, the standard value is negative. As the concentration increases, equilibrium will shift to the right, and E naught will also increase. Make sure you absorb this fact and understand it properly. So look at this graph now. This graph is going to show us is more an explanation for that statement that we just made. You can see the value for our standard electrode reduction potential for zinc is a standard value. You don't need to memorize it, minus 0.76, and for copper is 0.34. Of course, both of them coming to meet on 0 on the x-axis. So this is their graph of their concentration of their electropotential against time. This is a graph of the electropotential against time. Okay, so apply to next equation where we have our E to be equals to E naught plus RT over NF, ln of the reactant ions raised to the power of their number of moles, all over the product ions raised to the concentration of the product ions raised to the power of their number of moles. This is our formula that we already established. When the system achieves equilibrium at room temperature, next equation is simplified to this value. If, of course, we said if it achieves equilibrium at room temperature, the next equation is simplified to this value. E is equals to E naught minus, you can see now the value here is not plus, the value here is minus 0.059 all over n. Why is the value changing to minus? You can see in our correct next equation, we have concentration of reactants all over the concentration of products. Now, in order to make this part look like our equilibrium constant, we want to relate our next equation to our equilibrium constant. We have changed this from being reactants, concentration of reactant over concentration of products, to concentration of products all over concentration of reactants. And of course, once you flip a value like that with logarithm, the outcome will become negative. So in order to adjust the value that will be changing here, we have changed our sign here from positive to negative. If you want to understand you want to appreciate what I'm talking about here properly, you can just pick your calculator and find the log of 10 and find the log of 1 over 10. Both values will be the same. The only difference is the sign. The log of 10 and the log of 1 over 10 would be the same, but we have opposite signs. So in order to balance that sign, that's why we have put a negative sign outside here. So it's the same next equation, just that we flipped these two in order to be like our equilibrium constant. And since we said equilibrium constant is concentration of your product, Kn2 plus in this case, Zn2 plus all over concentration of your reactant, which is Cu2 plus in this case, and at equilibrium, E cell will be equal to 0. At equilibrium, the E cell, that is the electropotential of the cell, will be equal to 0. So the implication of that now is that this value will be 0 in our next equation, E volts. E here will be 0 volts, which is equal to our E naught, standard electropotential, minus 0.059 over N log Kc. Are you seeing how the formula is coming? Now, don't memorize this formula because you might not remember it. Once you can remember the next equation formula, you can always find your way to this formula. So that is the formula we are going to be applying when we want to solve for our, when we want to use our Kc, which is our equilibrium constant, to solve for our E naught, or when we want to find our equilibrium constant using the value of our E naught, which is your standard electropotential. Let's see some examples to buttress that point. Let's consider the following reaction. This is 2Fe3 plus Cu to give you 2Fe2 plus aqueous plus 2 plus Cu2 plus aqueous. Now the question says calculate the E naught of the cell and calculate the equilibrium constant Kc for the reaction. So you have to calculate these two values. This is the whole question. You are given this equation and you have to calculate for the E naught, which is the standard electropotential of the cell, and you have to calculate for the Kc, which is your equilibrium constant for the reaction. How do we go about this? First, I need to break them to half cells. Don't worry, these values for the half cell will be given to you. All you need to do is write out the equation. I can see that F is moving from 3 plus to 2 plus. Automatically, that's telling me that it is a reduction reaction. So I write out the reduction reaction, Fe3 plus E minus to give me Fe2 plus. The E naught for this reaction is 0.77 volts. Like I said, it will be given to you this particular value because it's a standard value. For your copper, is moving from copper solid to copper 2 plus. So if I write the equation, that will be Cu to give me 2E minus plus Cu2 plus. Of course, I'm using E minus in order to balance the 2 electrons here so that it can become 0, like what we have on the reactant side. And this is our E naught that corresponds to that. The overall reaction for this particular equation now, in order to balance it, I need to multiply this through by 2, this first equation, and see because this is 2 electrons here, and I'll multiply the second equation through by 1. That doesn't change the equation, so I don't need to bother myself with that. So if you multiply this through by 2, we are going to have 2Fe3 plus. Of course, this becomes 2E minus. Both of them cancel each other out. And then I join the 2 equations together. I'll be having 2Fe3 plus Cu to give me Cu2 plus 2Fe2 plus. Okay, so the E cell will just be the sum of this plus this will give me plus 0.43. This, so that's plus 0.77 plus minus 0.34. So if you do that, we are going to have plus 0.43 volts. Having gotten all those information, in order to find, we can easily find our Kc now. We have to find our Kc. We know that our Kc is equal to the concentration of the product, concentration of the product raised to the power of their number of moles divided by concentration of the reactant. So concentration of the product in this case, our product here is Fe2 plus, and see both of them, there's no solid here, so we will include both of them in the equation. So raised to the power of 2, and then for Cu2 plus raised to the power of 1, then divide this by that of the reactant. In the reactant, you can see copper is a solid, so we will not include it in this equation. So we just have Fe3 plus raised to the power of 2. Okay, now bringing this on to our next equation. Don't forget from your next equation, our E cell, which is going to be 0 volts. We've already established that the value will be 0 volts at equilibrium. So it means this value is 0 volts is equals to E naught minus 0.059 all over N. Our N in this case is 2. The number of electrons that was exchanged. Don't forget we multiply this 2 by 2, so this one too will be 2. So the number of electron exchange is 2, so this will be 2 log of Kc. Okay, so if I punch this correctly again, I'm going to have 0.43, which is the value we've gotten here, minus these values, log of Kc. So do the math. If you do the math correctly, what you need to do here is just divide 0.059 divided by 2, you get a value. Now take this O, on this other end we have 0, so we can take this O value to the other side so that we have log of Kc. You know, log of Kc will still be carrying the division of 0.059 all over 2. So you have to divide both sides by that value to have log of Kc standing alone. So if I divide both sides by that value, I'm going to end up with log of Kc equals 14.59. 14.59. Now, to make Kc stand alone, I need to find the antilog of 14.59. In order to find the antilog of 14.59, just pick your scientific calculator, click the shift button, and then press the log. It will give you the antilog, and then you put 14.59, and then if you put the equality sign, it's going to give you 3.77 times 10 to the power 14 mole per dm cube. So this is what we call the equilibrium constant. So that's the value you are looking for. Is as simple and as straightforward as that. Lay your hand on this other one and solve it yourself, and let me know when we are discussing. Let me know how you find the question. This is also just almost the same with the one I just solved for you. So lay your hands on that example. Okay, so we're almost done. This is going to be the last under our next equation. Next equation and solubility product. We look at next equation and our equilibrium constant, and then we'll be looking at our next equation and our solubility product. So that's KSP. That's Kc, this is KSP. Similar to calculating equilibrium constant, solubility product of a sparingly soluble salt can also be calculated in the same way mentioned above. That is the same way in which we have discussed in our equilibrium constant. Now let's consider the solution of silver chloride. Silver chloride salt can dissolve to give us a silver plus aqueous plus a silver plus ion. plus a chloride ion. What will be the half reaction for this? For the half reaction, our HCl plus C minus give you HCl plus Cl, you have your 8 or minus. These values, be able to try to memorize them. Overall equation of course, this time we saw this, we are going like this value. So using this equation, you can see I'm using this reaction, so don't forget that that's what I change value from positive negative. So here it's negative because I'm using product followed by hand. So this is the same one I'm doing all along. And then we get chemistry equal. Okay, so for the KSP of Ag plus concentration, AgCl solid, you can see the KSP is going to be the concentration of the product. Our product here is concentration of Ag plus and Cl minus. Divided by the product, in this case, you can see the product is a solid, so we are not having any product. Product is 1. So if you insert this into the equation, we are going to be having this E naught minus 0.059 over N log of this value, which is this, is the same thing as your what? KSP. So this is your KSP, which your solubility product. You can see we are not including reactants at all when we are talking about the KSP. You will understand this better when we solve 1 or 2 examples. At equilibrium, E will also be 0. So replacing in the equation, we'll be having 0 here, just like we had in our previous one. If I solve for KSP, how to go about it, take this to the other side. Okay, if you take 0.5 minus 0.58, it becomes plus 0.58 on this side. I still have my negative sign here. So all I just do now is find the value of this. Of course, this is 1, so it remains 0.059. Divide both sides by this value so that log KSP can stand alone. Like divide both sides by these values, I'm going to have log KSP to be equal to this value. This is just simple mathematics. So to find KSP, I'll find the antilog of this value. I told you how to find antilog. So if you find the antilog, you are going to arrive at this value. So make sure you pick up a calculator and try this out yourself. Now, the question may be extended to calculate the solubility from the solubility product calculated, okay? So note that E naught is always negative for sparingly soluble salt as KSP is very small. So for sparingly soluble salt, E naught will be equal to what? Will be a negative value. So let's see a practical example. Example now, we are given a mercury chloride. The mercury chloride will give, if mercury chloride dissolves, gives you your Ag and Cl minus, which is your silver and Cl minus. And also, you know, you have Ag2 plus 2A minus plus Hg. So if you calculate for the KSP for AgCl2, you'll be given those 2 values always. So oxidation reaction now would be this, your Ag to give you Ag2 plus 2E minus, which you've been already given in the question. And then your reduction is going to be your AgCl2, and see the way I did it in the previous one, plus your 2E minus to give you Ag plus 2C, which will also be given. Those values are always given, so you don't have a problem. Sum them together, you have this. Input them in the equation. We are looking for our KSP in this case. So just input those values and then solve mathematically, you arrive at this. So next equation and pH of a solution. Next equation and pH of a solution. Under the standard hydrogen electrode, if the solution of H plus is not 1.0 mole per dm³, the E cell can be calculated using the NERNST equation. So normally, when we have a standard hydrogen electrode, it's supposed to have a E cell value based on 1.00 mole per dm³ concentration. And we said that before in the previous class. But what if the value, the concentration of the hydrogen ion is not 1 mole per dm³? Then we have to use our NERNST equation to determine that value, determine the, use the NERNST equation to calculate for our E cell, that is the electric potential of the cell. So assuming the metal is oxidized by the standard hydrogen electrode, the cell notation will be written in this way. If the metal was oxidized by the standard hydrogen electrode, then we'll have this cell notation. This is the metal, this oxidized to give you M2+, and then you have this represent our standard hydrogen electrode. I believe you still remember this. It's the constant way of writing your hydrogen electrode. You put your H plus aqueous. In this case, the concentration is not 1 mole per dm cube, so we represent that with X mole per dm cube with our H2 gas, of course, then with our platinum solid. We use a platinum electrode for our standard hydrogen electrode setup. So the overall reaction can be written thus. You have your M solid plus 2H plus aqueous to give you your Mn2 plus aqueous plus H2. And our E0 will be positive. Is that okay? The value of our E0 will be positive. We don't know what the value is yet, because we know our value must be positive. So E will be equal to E0 plus our formula as we have always used it. You can see I'm using reactant over product now. That's why I'm putting positive sign here. So if I should input the correct values, number of electron transferred will be 2. Okay. Our reactant is H plus raised to the power of 2, the number of moles. And our product is our metal raised to the number of moles. Number of moles here is 1. So if we have, we go ahead here, we have 0.059 all over 2 times minus 2. How do I get this minus 2? The minus 2 is the power here. Is that okay? This power here is brought down. It's brought down here. So when you bring the power, you can bring down a power from a log. This is just common mathematics. The power from a log, which is raised to the power of 2 here, we bring it down to become this value, and then we have our positive sign. Log of H plus is also known as pH. You don't have to memorize any of this. This is the formula you need. E is equal to E0 minus 0.059 pH. This is what you need to have in your memory, because you might be asked to calculate for pH. This is the relationship between the pH and the electrode potential. So let's solve one example. The EMF of the following cell at 25 degrees Celsius is 0.093 volts. Lead solid, of course, to lead 2 plus of this concentration. This is our salt bridge to give you H plus, which is our test solution. H2 gas with the platinum solid. Calculate the pH of the solution. So we're given the EMF at room temperature to this, and we're told what the pH, we're told what the cell notation is, and then we're asked to find the pH. So this is very straightforward question. The overall reaction in this case now, we'll be having our lead plus 2H plus to give you lead 2 plus. This is the reaction I'm writing out. Lead is our this here now, and this our reactant, this and this our product. So I just put that out, and our E0 is plus 0.13 volts. You don't need to memorize this. It will also be given. This is a standard value. So I insert my E0. I was given my the value for the EMF. Is that okay? So the EMF was given to me to be 0.093. So I know my EMF to be 0.093. So that's what I have here. All I did here was to make this the subject of the formula. I took E0 to the other side. Subtract your E, which was given, from your E0, which is what we have here. Then divide both sides by 0.059, and you get the pH of 0.63. So that is how to calculate it. So I'm going to send you questions so that you can lay your hands on. The questions I ask you to solve during the class, ensure that you sit down with them, solve them on your own, test yourself. When I send you assignment also, ensure you do them on your own independently. And most importantly, make sure you are punching the calculator yourself, because many times the problem students face with these calculations is they think they know how to calculate it until they sit down with the calculator themselves, and then they are getting the wrong values, haven't done the correct calculation. So try your best to ensure you do the calculations yourself and know the correct mathematical operations in punching the calculator, how to use the anti-log, the logarithm, subject of the formula. All these are basic mathematical principles. So go and revise those things and make sure you know them well. So thank you very much. Next class, we shall pick it up from here and we shall begin to discuss our Faraday's law.